Alright, so today is day 68. I solved 3 more lead code problems. I did these 2 hard problems, minimum window substring, sliding window maximum. They are quite difficult. And this one, linked list cycle. We are sitting now at 36 out of 150. So let's go ahead and redo them again. The first one, it's this one, minimum window substring. So let's read it. Given two string s and t, return the shortest substring of s such that every character in t, including duplicates, is present in the substring. If such a substring does not exist, return an empty string. Alright. So in this one, I remember that that the solution, what was the main intuition? That we're gonna have a window over s. And the main thing is that, because I remember how I tried to think about it, is that let's say we have this window, and what we want to say at every window is to check if this window is valid. So what makes a window valid is if a window is a substring of t. So, but in order to know if it's a substring of t, we would need to count, to iterate over every element in the window. And if we do this for every window in S, this is too much complexity. So the trick here was to use another variable that keeps track of the characters that have been satisfied, right? So the way to do it is that first we create like a frequency hash map, and then at every time step that we move the window, we check, we update this tracking variable that tells us how many characters are satisfied. And if we satisfy enough characters, we can update like the global tracking value. Alright, and yeah, in the end we return the value and that's it. So, and mostly all of the sliding windows problems can be reduced to this like kind of boiler template. So we're gonna have like a left pointer, and then we're gonna have like for some sort of this, in this case is s. So we're gonna have a left pointer, a right pointer, this is gonna be the window. We're gonna do a for loop, and the right pointer is gonna be increased. We're gonna have like some sort of shrinking condition that we're gonna do to move the right pointer. So in this shrinking condition, we're gonna do left plus equal 1. This shrinking condition, if it's a very easy problem, is just an if statement. So it means that at every iteration, we just move one by one the left pointer. In this case, we are gonna do it while this until, yeah, that's a better word, until we find a window, a short window that is no longer valid. So it's gonna be a while loop, and it's gonna have the condition. I mean, for this we would need actually to declare like the two variables. I'm gonna say to satisfied, and it's gonna be okay, I actually need another 2 more variables, so I'm gonna create them now. Okay, so first let's create in the simplest way the hash map, the frequency hash map of t, which is gonna be just using from collections import counter and default dictionary. And with this we can create, this is gonna be like the frequency dictionary that we need to satisfy in the window. So I'm gonna say this is need, and this is the counter of t. And now we need the window dictionary, frequency dictionary, and this is gonna be default dict, and it's gonna have some integers. And with this we know that we have to satisfy every character in need. So to satisfy is gonna have length of need, and satisfied it's gonna be 0, and that's it. So now for the shrinking condition, it's gonna be if this is equal to this, and we're gonna move the left pointer, right? We're gonna have more logic, but I think we can stop now. Like, we can stop about this type of logic. So we're gonna do a window, we're gonna have a window, we're gonna increase the window, we're gonna have some condition to shrink it, and I think that so what do we need? First we need to fill the window, because we don't know what is actually in the window. So we can say window ch plus equal 1. So we are filling the dictionary. We are filling the dictionary and saying the first, for the all we have one element, and then the thing is that we need to check if this element is in D, because if it's in D, then we can update this amount of requirements satisfied. So I'm gonna say if character, if character in D, I mean in init, because it's more efficient to search directly in the hash map. But this is not exactly the case, because in this case there is only one incidence of X. But what will happen if in T there are many X's? We would need, the thing is, like, I mean, in the case that in S we have more X's than in D, we don't want to increase the amount of characters satisfied. We only want to increase them for the first iteration. So I can say if, I mean, given that we already update the frequency here, the frequency is going to be 1. So the first iteration is going to be when this is equal to the frequency in init. And we are going to update satisfied plus equal 1. And then we can shrink the value. And we're missing something here. We are missing, because if this is true, I was going to create another if condition, but if we have the while here, I mean, we need to do it inside the while. If this is true, it means that we have a valid window. If we have a valid window, we have to compute at the beginning of each while the best window, the size of the best window. So I'm going to say this is going to be best, the length of the best window, and the best window, the beginning, should be the worst, which is going to be infinite, float of infinite. And given that we need not only the length but actual the position, then it means that we want to keep track of the pointer. So the pointer is going to start at 0. So if this is true, we want to know if the current length, which essentially is right minus left plus 1, is less than the best length, which is going to be true for the first iteration. We have to update best length to this value, and then we can update the pointer to a current left, right? Okay, and now what? Now the problem is, when we are shrinking the window, it could be the case that we are shrinking it to a case that was making the T. So if we had like this, I don't know, like if we have like some window that make the window valid and we exit like some character, now the window is invalid, so we need to remove from satisfy that now one character is not satisfied, and this is going to be true. Okay, first let's update the window after shrinking. So once we shrink the window, it means that the character stored at left, I'm going to call it left, it's going to be S of L. So the character stored at left, we're going to remove one, and then we have to check if after removing the character we realize that we don't have enough enough frequency to require to fill the requirements, then we are gonna remove when satisfied, right? So if it's greater, it means that greater or equal, it means that it covers. So if it's left, now we need, if it's less than where is it? This one. Then need of left. Then we need to satisfy it, decrease it by 1. And in the end, we got to return this needs an indentation. I didn't see this. Alright, and in the end we gotta return, essentially it's if the best length never updated, because it's only gonna be updated it's if it enters to the while loop, and it only gonna enter to the while loop if it finds a valid window. So if there is no valid window, we have to return empty. So I can directly say if empty. I like this because it's a way of translating like a practical like ideas, no, like plain words ideas into practical intuition. So for example, saying like I want to check if there was a valid window. I can check if the best length didn't change. So if best length is equal to float infinite, it means that it never found a valid window. If it find it, then we have to return what it found. So it's gonna be s of we have to use this one because this is the pointer that we saved until the like how much was the window, which is gonna be best length. And let's hope, okay, we have it. Nice. Let's submit the problem. And we got it. Nice. Well, yeah, this problem was quite hard, really hard. Let's try to solve this one. Oh my god, this one is also very hard. But let's try to do it. You are given an array of integer nums and an integer k. There's a sliding window of size k that starts at the left edge of the array. The window slides one position to the right until it reaches the right edge of the array. Return a list that contains the maximum element in the window at each step. What was the intuition in this one? And k equals 3. Oh, I remember now. Yeah, this one is actually also very hard. We need to use like a DQ, and we are gonna keep it in monotonically decreasing order, and we are gonna return the element to the left of the queue. Okay, let's try to do it. From collections, import DQ, and we're gonna start DQ as DQ, and for I, x in enumerate nums, and we're gonna have to store the result in somewhere, so I'm gonna call it the res. And for ix in enumerate nums, so we're gonna have a window, but we are gonna do, essentially what I'm thinking out is that at every iteration we can append to the result the maximum, because once we reach the first 3 elements we can grab the maximum value, then I is going to increment and we are going to have another window and we get the maximum value, and so on. So at every iteration we can append, but only if we reached already the 3 elements. So how do I know if I reach the 3 elements? So essentially it means that I is greater or equal than k minus 1. Because if I is 2, k is 3, then it's 2 is greater or equal than 2, yeah. So res dot append, and we gotta append. Do we have to return? What do we have to return? We have to return the actual numbers, right? Or the indices. Let's see. 2, k is 3, the maximum is 2. Yeah, we're gonna return the actual numbers. Also in the queue, I think it's better to save the indices. Okay, so nums I, and then in the end we're gonna return res. Okay, and then how do we do the condition inside? I don't remember. Let's think about it. So we are gonna I think this problem doesn't resemble that much a sliding window. It's much more similar like to stack or queue, something like this. But okay, so this one is, we have the 3 elements. I think it's better if we start maybe from here. So if the element, we need to have a way of popping. Okay, we're gonna use a while loop somewhere here, because we need to remove the elements from the queue. So if we are given a new number, so it means that we move the window one more, and we find that this new number is greater than, we need to pop all the elements in the queue. So I can say that while the last element in the queue, so I'm going to say while dq minus 1 is less or equal than x, we have to pop, right? We have to pop dq.pop. And we need to also append, so I'm going to say the q.append, and we are appending the indices. No, but wait, this is also an index, and x is a value. So I have to say, instead of dq minus 1, I have to say nums of dq minus 1. dq pop, dq append I, and I need another more condition, I think. Okay, let's work through the example and think about it. So we have 1 to 1, so we find 2, so we have to pop 1, right? Then we have 2, then we find 1, then we find 0, then we find 4, so we pop 0, we pop 1, we pop 2, and we have 4, and we okay. What we have to check is essentially that after we increase the sliding window, we need to know if the value that was stored in the queue as the max value no longer is the max value because it's outside of the window. So if the first element in the queue, so it's going to be dq0, if dq0 is the first element, if the index of the first element is outside of the window, so it means that it's less than wait, dq0 is an index well, how do I compute the left? How do I compute the left? I mean, it's gonna depend on k. Okay, let's do it. Left is gonna be equal to, so if x, if I is equal to 2, then left should be equal to 0. So it's gonna be I minus k, it's gonna be the same, I minus k plus 1. If this is less than left, then we need to remove from the left. So I'm gonna say dq dot pop left. I think this is the method, I don't remember. And I think this is it. Okay, list index out of range. We can solve it with this. Let's also add it here. Basically, we're not gonna query this if it's empty, if dq is empty. There's an issue. Nums, and your output is 10426, is better output 22446. No, there is definitely some error in the logic. If dq okay, I don't know why there is a 1. dq is gonna be empty at the beginning of the iteration. This is also gonna be empty, so we're gonna add 1. This is not gonna be the case. Then at the next iteration, we're gonna, this is true, but then left is definitely, this is not gonna be less than this because left is negative. And then while dq is gonna have 1, then the last element in dq, which is still 1, the last element in dq, the character of the last element in dq, it's 0. I'm saying 1, but it's 0. Now this is 1, and 1 is less or equal than x, which now is 2, and 1 is less or equal than x. Yeah, this is true. We're gonna pop it, and then we're gonna append the 1. We're gonna append 1, and yeah, the issue is here. We need to append the first element in the queue, so it's gonna be dq 0. Okay, I thought it was something more complicated, but it's fine. We did it, and let's finally solve the last one, which is this one. It was detecting a cycle in list, and this one is quite simple, like very simple. I remember I did it with like a set, and I said like at every iteration add the node to a set. If you find that a node is already in the set, then you say that it's a, there's a cycle, otherwise it's false, right? But I saw that there is an algorithm, so you're gonna have like 2 pointers, and a slow and a fast pointer, and at here both of them are gonna point to the head, and you're gonna run a condition like while fast and fast.next, because the condition is that essentially you're gonna move fast 1 to the right, and slow 1 to the right, and you're gonna move fast 2 to the right. And if a slow is fast, so if both of them share the same node, then you're gonna return true, their cycle. And if you finish and you realize that you get to none, it means that there is no cycle, so you're gonna return false. So this is the problem, and I think the algorithm is like very nice because it's like modular arithmetic. Yeah, because the way to think about it is like, you can think about it as if you have a clock, and then essentially the difference between the fast pointer and the left point and the slow pointer is 1, and this difference increases by 1 modulo k. So essentially you're gonna traverse to all different combinations of the possible differences until the difference is gonna be divisible by k, and it's gonna be exactly 0. So it means essentially saying that the residual after dividing by k is 0. It's saying that both of the pointers are going to end up in the same position. And that's it. Okay. So this was for today. I'm going to stop now.